All right, so part A asks, what is the geometric interpretation of the modulus of z? And when we see the word geometrically, that's just asking graphically on a Cartesian graph. Okay, so recall that for a complex number z of the form x plus iy, where x and y are real and I is the imaginary unit, meaning that I squared is equal to -1, we have that the modulus of z is the square root of the real part x squared plus the imaginary part y squared. And something that we can do with this definition right away is we can go ahead and square both sides. And when we do that, we're going to end up with x squared plus y squared equals a real number squared. And by making one little definition, by letting the modulus of z be defined as maybe capital R to be a little bit suggestive, we really have that x squared plus y squared equals r squared, which is the equation for a circle. And as such, we can graph it on the coordinate plane as follows, where the x-axis is really going to be the real part of our complex number z, and the y-axis is going to be the imaginary part of our complex number z. And so when we graph this circle, it's going to have center at the origin, but then it's also going to have a radius, which is exactly the geometric interpretation of the modulus of z. So that answers part A. All right, next we have to show that if the modulus of z is equal to 0, then the complex number itself has to equal 0. And so going back to what we said graphically about the modulus of z, that represents the radius of a circle that's centered at the origin. And recall that the definition of a circle is simply the locus of points that are a distance r away from the center. But remember, we said that we defined r to be the modulus of z. And if the modulus of z is 0, then really our circle is going to be the locus, or the set, of all points a distance 0 away from the center, which is the origin. Okay, and the set of all points a distance of 0 away from the origin is just the single point, which is the origin. Which means both x and y both equal 0, which means the complex number z, which is x plus iy, is going to be 0 plus I0, and because of the way multiplication and the complex field works, is defined to be the 0 element. That's part B. All right, next up we have to show that if lambda is any whole real number, then the modulus of the complex number lambda z is equal to the absolute value of lambda times the modulus of z. Okay, and just to make sure that we're on the same page here, lambda z is going to be a complex number, and we're taking the modulus of that, so that's a real number. This is the absolute value of a real number, which is a real number. And of course, the modulus of z is a real number. So all of these are real, and the product of real numbers is, of course, real. So everything kind of checks out there. Okay, so to do this, we're just going to do it straight from the definition. So we're going to, again, go ahead and let z be x plus iy. And the complex field has scalar multiplication very simply defined as distributing lambda to the real and imaginary parts. So we have lambda x as the real part, and we have lambda y as the imaginary part, which means that the modulus of lambda z, by definition, is going to be the square root of the real part squared, this real part squared, plus the imaginary part squared. Okay, and when you work that out, you're going to get a lambda squared that's going to factor, and then you're going to have x squared plus y squared left over. Okay, we're going to go up here, and this is going to be equal to distributing the square root to both the lambda squared and the x squared plus y squared term. And now what is the square root of lambda squared? Well, you might think that it's lambda, but that's actually not true, right? If I have the square root of something like -2 squared, You might think that that's equal to -2, but it can't be. The square root is a function, and all functions need to be what's called well-defined. That means for every single input, there must be exactly one output. So you can't have the square root of something be a -2, because then it could also be a +2 with order of operations. If you just square the -2, then you get the square root of 4. And there are technically two things that can multiply together to get you a +4, plus and -2. Okay, but we can't have both solutions, right? And so to ensure that our answer is only, say, positive, then we put it in those absolute value bars, and we call that the principal root. Okay, so the square root of lambda squared is the absolute value of lambda to ensure that we're only getting one answer. And by definition, the square root of the real part squared plus the imaginary part squared was the modulus of z. All right, part D says if z1 and z2 are complex numbers, prove that the modulus of the product z1 times z2 is equal to the product of the moduli of z1 and z2. We also have to prove that the modulus of the sum is less than or equal to the sum of the moduli. Okay, so this latter inequality is really so famous that it's called the triangle inequality. And I'll talk more about this probably in the next video, but we're only, I think, going to prove the first one. And so we're just going to do this from the definition, but we need to establish a couple of definitions first. So we're going to let z1 be x1 plus I y1, and z2 is going to be x2 plus I y2, where, of course, x1, x2, y1, and y2 are all real numbers. And, of course, I squared is -1. Okay, so let's try to do this from the definition. And so we really have z1 times z2. So let's work with that. So we have, first of all, let's just take the product. And z1 times z2 is going to be x1 plus iy1 times x2 plus iy2, which when you FOIL that out, you should verify that you're going to get a real part that is going to be equal to x1, x2 minus y1, y2. If you're curious where this negative sign comes from, it comes from the fact that we're taking this times this. And remember that I squared is a -1. Okay, plus I times, and then the imaginary part is going to be x1, y2 plus x2, y1. Next up, to take the modulus of this, remember the modulus is going to be the square root, big long square root, of the real part squared, this real part squared, plus the imaginary part squared. And we're just going to have to FOIL this out. Okay. So this is going to be equal to x1 squared, x2 squared, minus 2 times the product of x1, x2, and y1, y2, plus y1 squared, y2 squared, plus the second term is going to be x1 squared, y2 squared, plus 2 times the product of x1, y2 times x2, y1, plus x2 squared, y1 squared. Okay, and then the nice thing about this is that two of those terms cancel, right? This term and this term both have an x1, x2, y1, y2, and they're both inverses in sign. And then this is going to equal the square root. And I'm going to write the terms in a bit of a strange way, but you're going to see why in just a second. So I'm going to write this as x1 squared, x2 squared, plus, and then I'm going to take the third term right here, x1 squared, y2 squared, then the fourth term, x2 squared, y1 squared, and then finally the second term here, y1 squared, y2 squared. The reason I want to do that is since I have 4 terms, I might try factoring by grouping. Let's see if that works. And so I have that this equals, Well, these first two terms right here, they both have an x1 squared, so I'm going to factor that out. And the stuff left over is going to be x2 squared plus y2 squared. Plus, and it looks like both of these both have a y1 squared that I can factor out. And I have the same thing left over, x2 squared plus y2 squared. Finally, I'm going to factor out that x2 squared plus y2 squared. And when I do that, the thing left over is going to be x1 squared plus y1 squared. Okay, and so we can distribute the square root just as usual. And we get that this is equal to the square root of x2 squared plus y2 squared times the square root of x1 squared plus y1 squared, which by definition is the modulus of z2 times the modulus of z1. And since moduli are just real numbers, the real numbers have commutativity, and we can swap the order of these moduli. And so ultimately we just showed that the modulus of a product is really just the product of the moduli.